multiple rings? What happens if we have heteroaromatic rings? What happens if we have both? Damn. Okay, let's try this one. Pyridine. What happens if I nitrate this? Nope. Think about what we just did in the previous example with a basic nitrogen, like this one. What happens to it before anything else? Bases react with acid. Nitration is an acid conditioned reaction, exceptionally acidic. It's going to get protonated. Now where's it going to go? That's not part of the resonance, because it's using a lone pair that's not part of resonance, but it puts a cation on one of the ring atoms. So where's my nitration site?
The meta position of the carbocation.
So you mean 2 carbons away? Why?
Or just follow the route. Carbocation directs it to the meta position. And also when you do the rest.
Well, technically, meta position, your cation is going to be out here. So you're talking about meta to that, which is 1, 2, 3 atoms away. Here you're talking about 2 atoms away. There. Why? Draw the intermediate. Ortho and para directors are ortho and para directors because they resonate a cation to that ortho or para position. Which means if I try to nitrate this ortho or para, I'm going to end up trying to resonate a second cation onto a nitrogen that already has one. You think 1 cation is bad, try putting 2 on the same atom. No. The meta position would resonate a cation right next door to that, which is still bad. But at least it would work. Nitration will go to the 3 position where I have the arrow drawn only. So when I'm done, I'll have this. But because there is no intermediate going to any nitration of this ring that doesn't end up with 2 cations very close to each other, this reaction is really, really hard to do. The yield is very, very low. And this is one of the only electrophilic substitutions that actually works on pyridine. It's very unreactive towards electrophiles because since it tends to be protonated before the electrophile comes in, you're talking about putting 2 cations right on top of each other or right next to each other. So every intermediate you could form here is very repulsive, which means those intermediates aren't likely to form, which means the electrophile is not likely to go in. The yield on this is something like 10%. It's a horrible yielding reaction. Okay. What if the nitrogen is not basic? And we probably would protect that with something, so we'll just put an R group there just to make sure we don't have a problem with that. But the lone pair here is part of the aromatic system. So now where's it going to go? Why?
Because the two double bonds will go towards the nitrogen, forming your. You're just following the double bond and how you flip it.
Okay.
So I'm looking at nitrogen with actually 5 bonds for either carbon beside it. Then the two carbons, the two carbons on top, then that will be the reactive one.
Well, let's say that we went here with our electrophile. That's the 2. This would be the 3. Give me a reason to prefer one over the other. I didn't say flip a coin. I said give me a reason. Why? That's true of both. Is it not? So, it's a ring. All right, let's try resonance structures. That one. Put the cation here. That. Puts a cation here. So for that, I have 3 contributing resonance structures, right? Okay. What about the bottom one? If I bring that in, wow, that's atrocious. Let's try again. That one. And then if I bring that in, then what? I have to move this back out, which means this would be what I would get. Because I can't bring a 5th bond into the nitrogen, it already has 4. So to bring one in, I got to let something go. That's going to put a lone pair of electrons there. And it's going to give me an extra charged atom. That's ugly, very ugly. First rule of resonance structures. Well, first rule, don't use the sigma bonds. Okay, fine. Resonance is pi bonds and lone pairs and empty I orbitals only. The first real rule, though, is that your resonance structure, generally speaking, should not have additional charged atoms. There are cases where we'll do that just to prove a point, but if you can't draw a resonance structure at all without generating more charged atoms, that's probably not completely reasonable. This No. So what I have at the top, 3 realistic resonance structures. The bottom, only 2. So where's it going to work? Adjacent to the nitrogen. This is what happens. This happens, but only to a minor extent. Now, the reason I'm showing you this is not that I care about doing heterocyclic chemistry, that is, aromatic rings with non-carbons in them. It's that I want you to see that the rules don't change. The rules are exactly the same. Okay, now let's make it worse. Oh, crap. Now not only do we have to figure out, starting with which ring it's going to go into, then we have to figure out where on that ring it's going to go. That's not going to be fun. Or is it? This is indole, by the way. Nucleus of the tryptophan and serotonin molecules. So, for starters, which ring's going to get it? The 6-membered ring or the 5-membered ring? Why? The 5-membered ring doesn't have significant strain compared to 6, really. Not like this. A little, but it's not really that much. I draw it like it's more strained than it is. It's not really a 90-degree angle at the top. That's just a drawing convention. And strain really doesn't play into this. Not with that size ring anyway. So, right answer, wrong reason. Yes, the 5-membered ring. No, it's not a strain thing. Why? What else is there? Consider the electron density of benzene, 6 pi electrons over 6 atoms, versus pyrrole over here on the right board, 6 electrons over 5 atoms. The 5-membered ring's a little bit more electron rich, if we consider it isolated. It's not really isolated, but if I want to think about it that way, well, then I have 6 pi electrons in the 6-membered ring, and I have 4 over those 3 atoms. This is a very wealthy ring compared to this, which would be normal for benzene. So it's probably going to hit the 5-membered ring. It does. Okay, now where?
Carbons above the nitrogen. First of all, the electrophile will attack a double bond. And that's the only double bond that we have in the 5-member carbon chain. Whether it's closer to nitrogen or 2 carbons, or it's already proven that it's going to go to the next carbon, carbon 2.
But it doesn't. It should. No, it shouldn't. And you can tell me why once you draw it out. If I have this versus this, Which one is preferable?
The bottom one.
But I just told you that's not where it goes. Why? Why is the top case better off than the bottom one? Attack at the 3 carbon, top right, instead of the 2 carbon, lower right. Why? No, it's the complete opposite. But why? This is a different case, and we have to consider this when there are multiple rings. I still have a benzene ring attached here. I still have an aromatic system that is still aromatic. And generally speaking, that's not going to break just for resonance. So what I'm looking at is, can I stabilize this without having to involve the 6-membered ring? In the top case, yes. In the bottom case, no. Because in the top case, I can involve this lone pair to help move that charge around without involving the 6-membered ring. At all. In the bottom case, I have no resonance structure whatsoever that'll let me do that. I can't do anything with that structure except break the benzene ring to resonate it. I'm stuck. It has no resonance structures that don't involve the 6-membered ring. So, top case wins.
So basically, whenever you have two rings, you just treat it as an isolated system.
If that makes any difference, yes. It will not always come down to a black or white, yes, it can resonate without the other ring, or no, it can't. Sometimes it will be neither one of them is good. You have to involve the other ring, at which point you can't treat it as an isolated system. You have to then work for it. Okay.
Sir,
Yes?
what about the middle? Can this one resonate, this thing? The double bond in the middle will go towards the...
Yeah, but that involves the 6-membered ring. You no longer have a separate benzene anymore. And that's not unreasonable, but it is a lot harder to do. Okay. So, I'm just going to put a methyl group here to make my life easier. Well, conceptually, it's exactly the same. Okay. So, let's say you have to make this. And this is why. This is serotonin. If I have an acetyl group here and a methyl group there, it's melatonin. So let's say I want to treat depression. I have to start making analogs of serotonin because classes like mine depress people. Okay. So I have to be able to take something like indole, starting from the methyl group, which is removable afterwards, but I'll put it in place just to make our lives easier for now. And I want to do that analog of at the top. How do I do it? Can I do it?
Not sure about the old first one. Single three-way mass. Sedation, just did that.
Okay. First group has to go in the 5-membered ring if we're doing electrophilic substitution. No choice in the matter. So we've got to hope that that doesn't mess up things for us elsewhere. As it turns out, in this case, it does sort of behave like a separate system. And so that deactivates the 5-membered ring, leaves us with basically a native benzene. Okay. So now what? Now if I want to do something electrophilic in the other ring, is it going to go where I want it to go? Now I have 4 different possible electrophilic sites, each of them with resonance structures, and I'm looking for what's going to be ideal. What's going to be ideal is a resonance structure that ends me up with a cation right here, because I've got this lone pair in the other ring to help me out. So what's really going to help me is something that resonates a cation to here. So 2 of the positions will do that, 2 of them won't. Which is which? And I should actually put the numbering up. These are carbons 4, 5, 6, and 7. The 4 and the 6 react the same way resonance-wise. The 5 and the 7 react the same way resonance-wise. The 5 is what we want. Does that resonate a cation to the right place? Which would be, if that were simple benzene, para to the 5 position, which is where I want it. Does that work?
You're looking at the cation at the bottom. You said the cation should be at the 8?
Well, it would be, it's actually called 8A, but yeah.
Then no, the 5 the 6 and 4.
Oh, I mean,
The way I have it drawn, we're going to have our electrophile here and our cation here. Yes. So, electrophilic substitution of the other ring will be more likely at the 5 and the 7 positions. So then how am I going to control the mixture bit? The 7 position is actually very hard to get to. Normally your adjacent groups rotate. This doesn't. It's permanently stuck in the way. So you're trying to get here. This is a pretty decent blocking effect. So this is more difficult than a normal ortho group to get something next to it. Making 7 substituted indoles is actually very difficult. Luckily, we don't care. We wanted the 5. We wanted the case that happens to actually work. So we'd have to do something like, since we have an acetyl group on the other side, we can't really do the Friedel-Crafts version because we'd kill both of them. So we have to nitrate and then reduce it down and oxidize it from there. which we can do. This is heterocyclic chemistry. This is basically the beginnings of rational drug design, taking a known molecule, designing analogs of it based on its structure. Now, there's a lot of analogs I could think of, but the first ones you would make would be very, very slight modifications of whatever the natural thing is, because you don't really know how it works. So you'd start by saying, okay, what if this chain was 1 carbon longer? What if this was an oxygen instead of a nitrogen? What if this wasn't there? That's the lazy man's, because that's hard to put in place. You hope that one works. It doesn't. What if there's something else there? Well, if there's something else there, I get sleepy. Melatonin has something else on that oxygen instead of a hydrogen. Then you try things around here. Then you might try switching this out for an O or an S. Then you might try putting something here or here or here. And eventually you'll find things that actually work. If you took models of like Prozac or Lexapro or any of the typical serotonin drugs, you can pretty much take them and rotate them around and get them to line up with most of the atoms here. They are that close structurally, at least in one conformation, to the original signaling molecule. They have to be, or they won't fit. The crazy ones are when you start locking this down to the other ring. That's LSD. Is when this is locked down over here and there's something else on top of it, you get a completely different effect than if that's open and flexible out. A very weird effect to many people. So, we'll continue with this next time.